How do we begin to think about the infinitely small? Science and technology are beginning to take us there.
Hello, my name is Michael Motion. I'm a juggler.
I've spent my whole life exploring science and mathematics. Science has been a major inspiration for my work. I use physical skills to explore the unknown. Scientists use technology. Today I am inviting you to travel to a new world, the world of the infinitely small, the world of the nanoscale. The nano in nanoscale comes from the Greek nanos, or dwarf. All of our futures may depend on what we can learn from things like gecko's feet. One of the most unexpected examples of the power of nanomaterials comes from a small lizard, the gecko. The fantastic adhesive power of a gecko's feet is due to nanoscale hairs that allow them to stick to almost any surface in any condition. Researchers are creating a tape that mimics the bottom of a gecko's feet, with billions of tiny hairs. A waterproof adhesive based on this concept has been developed that could improve bandages and be used for internal stitches in surgery. But how can we get an idea of what scale we're talking about?
Let's start with 1 meter squared.
As we zoom in, the number at the bottom indicates the length of each side of the square. And now we move closer and closer to my hand, so that the scale is now 1/10 of a meter. Through the skin, to the skin cells, we are now looking at 1/millionth of a meter. And as we go deeper into the individual cell, we pass through DNA molecules, the genetic code in every one of our cells. We are now measuring in nanometers. 1 nanometer is 1/billionth of a meter. This is the nanoscale. And in this square with the sides of 10 nanometers, what we see are atoms. Each red dot represents a nucleus, and the orbiting white dots represent the surrounding electrons. There is another way to think of the trip we've just taken. If we were to imagine a trip of the same distance in our macro world, it would take us from the edge of our solar system all the way to Earth, to my house in Connecticut, and back to where we started. Our curiosity has led us to explore the vast expanses of our universe. Now we have new tools to investigate the promising realm of the nanoworld. First, how can we even see nanometer objects? Ordinary microscopes aren't strong enough. We have had to develop new tools, such as the scanning tunneling microscope, or simply STM. The STM does not work like an ordinary optical microscope does. Let us look inside the STM to see how it works. Instead of using light to look at a sample, the STM uses an electrical current. It works like this. A sharp metal tip is dragged across the surface to be imaged. As the tip moves over the surface, electrons flow across the gap between the surface and the sharp tip. This is called tunneling. Let's take a closer look. As we zoom in to the end of the tip, we see that atoms are actually fuzzy objects. They look more like Nerf balls than they do like ping pong balls. The fuzziness is the electrons swarming around like a bunch of bees. If you bring the two fuzzy objects, the tip and the surface, together, the electron clouds overlap and the electrons can't tell which atom they belong to, the tip or the surface. So they are perfectly happy to move to the neighboring one. This makes it possible for a current to flow between the tip and the surface. A feedback loop maintains constant tunneling current by adjusting the height of the metal tip. So, the height of the tip gives a direct measure of the topography of the surface. So if the tip goes across an even row of atoms, the result is very smooth bumps. But if there is an atom sitting on the surface, which is bigger and protrudes above the others, you can see a bigger bump. The movement of the tip is translated into a series of points and lines, which the computer converts into images, which use false colors to help represent the topography on a nanoscale. Different heights are represented by different colors. Here are what some of the images look like. This is gold, graphite, iron on copper, and platinum. Through our senses, we know how these balls behave in the macro world. They follow the laws of physics, gravity, speed, etc. Let's say we look at gold.
This small gold ring has the same color and properties as this very large gold hoop.
We intuitively understand the properties and behaviors of everyday macro-scale objects because we see them in our everyday lives. But the nano world behaves very differently. For example, when we examine nanoparticles, we see that particles of the same substance can have different colors just because they are different in size. How can the same substance have different colors? Gold atoms, for example, arrange themselves in a regular way. The nuclei stack together in a lattice and remain stationary. While there are some electrons that are bound to just one nucleus, other electrons are shared among all the nuclei and move about freely between all of them. Now, if you start with a large gold particle, these free electrons have a lot of space to move about. But if you decrease the size of the gold particle enough, then you get a nanoparticle, and the free electrons are now confined in a very small space. This, curiously, results in a quantization of speeds, which means that the electrons can only move at certain fixed speeds. So for instance, initial speed, twice that, 3 times, etc. The color of a particle depends on the amount of energy its electrons absorb when they switch from one energy level to another. Since the difference between the energy levels depends on the size of the particles, the color depends on the size of the particles too. This is why a solution of 5 nanometer gold nanoparticles looks red, while a solution of 90 nanometer nanoparticles looks blue. You can create a whole spectrum of colors just by controlling the size of the particle. Nanomaterials also act differently depending on where the atoms are located in the lattice. Let's go back to the way macro objects work. If you imagine a gold cube, there are 2 places where you can find atoms, on the surface of the cube and on the inside. Let's imagine that the atoms inside are like the passengers in a crowded subway car. Passengers near the doors can get off the train easily, while passengers in the center are sometimes unable to move. That's what happens to atoms on the inside of our cube. They are so crowded by the atoms around them that they can barely move. The atoms on the surface, like the passengers near a subway car door, are freer to move because there are fewer atoms surrounding them. Macroscopic materials, ones that you encounter in your everyday lives, have proportionately more inside atoms than surface atoms. Therefore, their properties are dominated by the properties of the inside atoms. But nanomaterials are exactly the opposite. There are proportionately many more surface atoms than inside atoms. So most of the properties of the nanomaterials are dominated by the properties of the surface atoms. As a result, nanomaterials behave differently than macromaterials. It is these different properties that make the field of nanotechnology so promising. Here are some other examples of nanoscale objects with distinct properties. This one is called graphene. It is basically a single sheet of graphite. Graphene consists of carbon atoms arranged in a chicken wire type of structure. Experiments at Columbia University show that this structure is stronger than a diamond. You can take graphene and roll it up to make things called nanotubes, which again have striking properties, like high tensile strength, high thermal and electrical conductivity, and good elasticity. Carbon nanotubes behave like wires, but unlike any wires we have ever known at the macroscopic scale. Nanotubes can carry 1,000 times more electrical current than the equivalent gold or copper wire. For this reason, they may someday replace the telephone and power lines we have today. Another example of nanoscale objects are fullerenes. These look like soccer balls, but they are only a nanometer across, and they can be modified to target resistant bacteria and fight certain cancer cells. Nanotechnology research promises exciting discoveries, like new ways of delivering medicine in the human body. Scientists are engineering nanoparticles, such as dendrimers, to seek out and destroy cancer cells. This amazing technology is being customized to target drug delivery, to improve imaging, and to confirm the death of cancer cells in close to real time. Nanoparticles are being linked to antibodies that recognize tumor cells. Once they are taken up by the cancer cells, near-infrared light can kill only the tumor while leaving the neighboring healthy cells intact. Nanobioparticles could be engineered to latch onto a damaged neuron and then extend conductive dendrites to complete the nerve connection and restore its function. Packets of conductive nanobioparticles could fill spaces between neurons to repair spinal injuries. Dynamic armor, when struck by a projectile, could instantly transform a pliable material into a rigid armor. By rearranging the nanostructure of the material, it can absorb the impact of bullets to protect law enforcement officers, for example. The structure of the sticky hairs on the bottom of the gecko's feet can be synthesized into a material for equipment that would allow humans to climb even slippery, wet rock safely. Just as I am constantly working on new skills to open up new worlds for my work, nanotechnologists will manipulate the nanoworld to address the challenges of the future. The nano, the dwarf, is about to become the giant.